Okay, thank you very much, Jim. I'd like to talk about substructure and the scalar broadened image of pulsar 0329 with radioastron. And we had quite a number of collaborators where Misha Popov did actually most of the work. And so I would like to talk about, just a moment, I have to put my receiver in here. Talk about first where the pulsar actually is located in our galaxy so that we see actually the environment as part of the spiral structure of the galaxy. Then I'd like to go a little bit into history and tell you what early VLBI observations actually resulted in when the size of the pulsar, scattering size of the pulsar was supposed to, or was aimed to be determined. And then I want to go into our radioastron VLBI observations, show you what we reduced in terms of the size of the scattering disk, and then also have some derivations as to the distance of the scattering screen from us or from the pulsar. So first to the location, and this is what you can find on the web, beautiful Milky Way galaxies with different spiral arms, Perseus, and quite interestingly here is between these larger spiral arms the Orion spiral arm, and our sun is just located outside or inside on the inside of the spiral arm. Now where is our pulsar? The pulsar 0329 about 1 kiloparsecs away, so you see there's about 8 kiloparsecs, so that's 1 kiloparsecs away, and it's at 145, if you go to the previous slide, 145 degrees longitude, so this is 0 degrees, so we got 145 and we are in this direction, so 1 kiloparsec, and we get right to there, where this again is the enlarged image. And quite interestingly, so we are, when we observe the pulsar, we're actually looking through this kind of intermediate spiral arm there. So from that point of view, it's quite interesting to observe this pulsar. So first about the history. Early measurements started already in Canada, after the VLBI system was set up between Algonquin and DRAO, so in the 1970s, but at 408 megahertz, even on this large baseline, relatively large baseline for that time, of course, only 20 milliarc seconds upper limit was determined. Comes out that that is much, much too large. A few years later, well, actually 15 years later, with the, at that time, Newmark 3 VLBI system, which actually improved the sensitivity by 56/2 square root, what is it, about 5 times, something like that. So we could actually observe quite a number of pulsars and also obtain much better sensitivity. So we observed at 2.7 and then actually got a better upper limit of 1 milliarc seconds. Also an upper limit, it turns out that even that was actually too large to determine the size of the scattering disk. Well, you think that with VSOP you have a larger baseline, 25,000 kilometers. In that case, that was actually an imaging space system pioneered by the Japanese. And they got actually a scattering size of 2 milliarc seconds. So that's where we stood. And then we used a radioastron with this very elliptical orbit, and at that time we actually had an apogee of about 350,000 kilometers, so that's about the distance from here to the moon, very elongated. And so one could actually sample different or a whole range of projected baselines. That was the real advantage of it. By the way, I just want to make actually a little advertisement for our other experiment, namely a gravitational redshift experiment. Very interesting that the Russians conceived early on to put actually a hydrogen maser on this spacecraft. Not really necessary for 327 megahertz VLBI observations, but kind of interesting for 1.3 centimeter or 23 gigahertz VLBI observations. Anyway, first hydrogen maser in space, and so clearly one could actually do a gravitational redshift experiment. With one observation, we are now at the level of gravity probe A, which was it's still actually the best redshift experiment, and we hope to get actually much better in the future by taking all observations into account, and then actually perhaps get the most accurate measurement of the equivalence principle, which is a base for general relativity. Okay, so back to the scintillation project. So what did we do? We observed the 324 in 2013, 2014. And these are our baselines, 25, 65, 100, and 350. And at 92 centimeters, it's basically also, you know, in millions of baselines. So this is about 350 or 330 million baselines. So the lambdas in terms of baseline length. So it's quite a long baseline. So, and then we observed, of course, the pulsar, gated the pulsar, and just actually focused on this particular area here, which is the main profile. The pulsar has here another spike here and another spike over there, but we focused on this one here. You see that this was actually observed with Green Bank, with a 43-meter telescope at Green Bank, and it has, of course, a very, very good signal-to-noise in comparison to the 10-meter antenna on Radio Astron, which is quite noisy, but still you can actually see the profile there. Certainly you can see the profile, the main part of the profile. And we switched on and off and compared these two for calibration purposes. So what we got from the correlator were these cross-power spectra, and so with some Fourier transform gymnastics, I may want to call it, you get to this part here, which is what we used for the analysis to derive the size of the scattering disk. So there are some relationships between the cross-power spectrum, how to get from there to there, or from there to there. So this is what we actually then analyzed. Okay, and this is a typical example of this part here, of one of this function here, a distribution of spikes, of visibility spikes, as a function of delay and fringe rate. So you see that it's quite elongated, quite extended in this delay range and not so much in the fringe rate range. So we basically actually focused on the cross sections. So we cut through here through the maximum in fringe rate, and then actually forgot about the three-dimensional distribution, but just actually use the two-dimensional distribution. So basically cut through this whole distribution there. And that is what we now analyzed further. Okay, so this is a typical cut through that distribution. So you see you have only delay here, and it was at the maximum, at the fringe rate where we got actually the maximum. This is now in terms of baseline length. So this is a very short baseline. It's just Westerbork in Holland and Kalyazin in Russia, close to Moscow. And here we have the first short baseline, Westerbork Space Radio Telescope baseline, and you see that the spike is clearly actually diminished on this scale. This is all offset a little bit, but here it's the same spike for these here. Here we have similarly on Kalyazin and SRT, and you see the size of the spike is about the same for that baseline. So our calibration is about right.
How long is 20?
Pardon me?
20 is in what units?
20 is, yes, let me see, 20 is 20 million wavelengths.
Mega wavelengths.
Mega wavelengths, yes, yeah. And so here we have now Kalyazin and the Space Radio Telescope at 120, and you see that the spike actually is not pronounced there. We have a whole distribution here, but you have to take into account that this was magnified by factor 10, yeah, and here also factor 10. So if you decrease it, you're basically down here to this level here, and you cannot see any spike, but it's not noise. This is all signal, but it's statistically distributed signal. Okay, so we did, in order to actually get the scattering size, we performed two analyses to get actually the visibility amplitude as a function of baseline. So one was where we actually took for each of these scans the maximum, and for each of these baselines the maximum from the whole lot of scans. And the other was where we actually averaged all these scans for a particular baseline and then came up with this particular visibility amplitude as a function of delay. And so this is just an example. So there are two different. So basically, this should actually give smaller values, particularly for the long baselines, of course. So here we have now the plot of the visibility amplitudes as a function of the projected baseline in mega lambda. And so this is close to 1 here. And then we have here on these baselines about 20, 30 mega lambda, the visibility falls off. And then we have here also some other data which are all significant. Here from one analysis we took the maximum of the scans, and here we took the average of the scans. Okay, so what is the meaning of all this here? So here I just want to indicate that these data points correspond to the average of the scans. So we fit now a curve where this is very close to Gaussian as alpha, or basically Gaussian if alpha is 4. Now, with some theory that was done several years ago, this alpha is not necessarily 4, but with Shishov's paper, we actually took 3.5, so close to 4, so it's almost a Gaussian, but not quite. 3.5 plus minus 0.5. And with that formula, we got then actually this curve, this fit, and determined the size, 4.8 plus minus 0.8 milliarc seconds at 324 megahertz. So clearly, all these attempts at 1 gigahertz, 1.7 gigahertz, where we got 1 milliarc second, were of course in vain, because we expected 4.8, and then that's a factor, what is that, factor 5, so 25 times smaller, so that is clearly out of that range of earlier attempts. Okay, so what else did we do? Well, the interesting thing is actually that apart from this, we had these large baselines and clearly could actually observe now the amplitudes outside what we call the ensemble average visibility magnitude, and clearly saw significant structure there. And here are some theoretical values for the RMS of the fluctuations. Now, what does it actually mean? Oops. What does it actually mean? Here's a nice picture that Michael Johnson made in terms of simulations for a quasar 3C273. And there you can actually really see the difference between. Now, this is the simulation for an extended source, as it should say. Keep that in mind. We have a pulsar, and that is basically, almost an unresolved source. So for an extended source, but if you actually take this a little sharper in your mind, make it a little sharper, then you come basically to an image that should correspond to our pulse observation. So what is this ensemble average visibility amplitude? Okay, take your mind and smooth over this whole picture, and then you basically get the size of this ensemble averaged one. Well, what is this here? That's basically the little speckles in between, and we take that from a statistical point of view and can predict the sigma RMS, the expectations from diffractive and refractive substructure in this image. So, yes, so that is our result. And
Are you saying that your result is measurement is still a factor of several higher than any expectation?
Yes.
Even with that?
Yes, yes, yes. We could not actually in this paper explain it. Yeah, it was higher. this is 0.013, and here we have 0.2 between 0.2 and 0.3. Yes, a factor 2, something like that, for these averages. Okay. Yeah, and then we come to the distance of the scattering screen, and we assumed a thin screen, and that was all calculated. We plugged it into this formula. We had these scattering times from previous observations, and came up that the distance of the scattering screen for a thin screen is just in between the pulsar and our observation. Well, for a little more complicated model, Shishov considered two-component scale, small turbulent and large scale refractive, and by sticking in all these velocities here for the pulsar, for the screen, for the observer, and the diffraction pattern, and I have given here a list of them. This was assumed screen standing still, observing from the solar system in the galactic. This was measured. We come to about, well, similar, 0.63. So what does that mean? 0.6, that's our average value. So here's a pulsar, here's our observing screen. So this is 0.5, that's 0.6 here, closer to the pulsar. How does it compare here? Well, you see here, this is our standpoint, that is a pulsar. Well, this is actually exactly 0.6. Whether that is real, I'm not sure, but it is quite interesting to actually look at it from this point of view. Okay, thank you very much. We did not see any arcs. We looked.
No, but is the S, is your 0.6 value consistent with one of the arcs?
Oh, I see. Yeah. Okay.
Robert.
Yeah. So when you compute your visibility values in those plots, I'm not quite sure how to interpret the ones that are fully resolved. Am I correct that you get that scattered visibility as a function of tau, you have a bunch of peaks, and then you select the maximum at those points?
Yes. So we have to get back to this plot here. So this is what we get over here. So that's a function of delay and fringe rate. Then we actually look close to 0 and find actually the maximum in the distribution, and then make a cut through that and consider only those two-dimensional plots then. Okay, so then we have two possibilities. We go to one observation and look at all the scans and actually take the maximum, then a long delay, and we can actually average all these cross-correlation, these functions, which is done here, and then take that maximum. So this maximum is a little smaller. And so we plot actually this averaged, the maximum from the average function, and then the maximum from all the functions over there. So.
Other question? Yeah, Vern.
So can you explain for us the decrease in the spike amplitude of the visibility? Is that what's being plotted here?
See, there was more. Oh,
In your
over here. So this is pretty clear. There we just don't have to average anything. We just actually take this maximum there. That's pretty constant. So that's a short baseline. And there we have all these data points. You see, there's 1, 2, 3, so several data points. They hang all together. Here also where we see clearly a spike. So here on these baselines.
You're plotting on the same curve, the height of the spike.
It's just the resolution of the source, I think.
Right. And then the other points come from the envelope of noise.
These points come now from the envelope of noise. Yes, but we are not taking, we don't fit a function or something like that. We are taking actually the maximum. And we also average these for one baseline here, for instance. We average these here, that is shown in this picture here, and take then the maximum. Clearly that later process results in smaller amplitudes. So, well, we actually plot both. At this point, we thought that it gives us a good range of where the amplitudes are for these long baselines.
But you're comparing the height of the spike for the short baselines with the height of the distribution of points along the way.
Yes, that's correct.
I think this would be an excellent topic for discussion. It is technical. So if there's one more question.
What about the distribution of spikes, visibilities, and of the amplitudes? There is a beautiful theory in the distribution of visibility and amplitude. Is that consistent with the theory of Hammond?
Let me see. Well, this comes actually from from the theory. So, as indicated before, these measured amplitudes are a bit higher, a factor 2 if you take the average, and well, here these are pretty high because we take the maximum from all the scans. So there is a discrepancy. We don't know the reason. Perhaps Michael has more thoughts in the meantime about what the reason may be, but at this point we didn't find a reason for that. It's a factor 2. Okay, thank you very much.
So let's thank Corbett again. Okay, the next talk is a remote talk by Olaf Lundin, resolving an interstellar echo with low frequency interferometry. And I assume we're ready to go. Almost.
Okay, so let me connect the video and the speakers, and then I'll say just go ahead, and then you can start.
Yeah, you get different average correlation levels. And they'll be different for the main pulse instruments, I would think. It would affect the...
Okay, Olaf?
Okay, we're ready?
Olaf, can you hear me?
Yes, I can hear you.
Okay,
can you
go
hear
ahead.
me?
Yeah.
Okay. Thanks a lot for giving me the opportunity to give this talk remotely. Originally, I meant to go to the workshop as well, but unfortunately, I couldn't now. Just 10 minutes ago, my computer completely crashed, so it's up and running now again. I hope this doesn't happen again. Maybe related to my camera, so I decided not to switch it on again. So this talk is about doing VLBI on an interstellar echo. So can we go to slide 2? This is the overview, so I want to start with a brief introduction of LOFAR, particularly about the German part of the array, then come to this ghost, this echo, and a certain pulsar, and then discuss what I'm doing VLBI-wise on this system. So on slide 3, we see an overview of the LOFAR array. This is a map of Europe, and we see all the LOFAR stations as green pins here. Most of them are in the Netherlands, where they are bunched very close together, so you cannot distinguish them anymore. There are also 6 in Germany, and we started using only these 6 stations, but later included others as well. And high up in the north, you can see in this corner between Finland, Sweden, and Norway, this white pin, which is the Kyra station. It's not a LOFAR station as such, but it has almost the same hardware, only it's not connected to the network of LOFAR. But we can also use this station for offline VLBI work. On page 4, just to show a nice picture, I show our own observatory in Effelsberg with a nice 100-meter dish, and to the lower right of it, the LOFAR station with the low band antenna field and the high band antennas as well. So this is one of the stations that we are using. On slide 5, I show again all the German stations, just because we start with this part of the array. So these are the 6 stations that we have available. And on the right-hand side, the baseline lengths and the corresponding resolution that we can achieve at frequencies around 150 megahertz. And this is our best frequency where we have the best sensitivity and also where the system is most stable. And we see that even with just the German part of the array, we can reach resolutions below 1 arc second. And once we include other stations, of course, this gets much better. And also the UV coverage gets better. But we started with just this part. And what I show in the following is just from these few stations. So slide 6 gives an overview of what we are generally doing with these stations. So most of the time, they are used as part of the international LOFA array to do interferometry, together with the other stations where data are correlated in Groningen centrally. But on the weekends, we have the stations to our own disposal, and we can do basically whatever we want. And mostly, we are using them to monitor pulsars for pulsar timing. This is done mostly to study the ISM, because that's, of course, a strong effect at low frequencies, but also to study polarization of pulsars and so on. So we have these 6 stations, typically for 3 days per week. And the great advantage of this is that we have extreme high flexibility. So if we have some idea on Thursday what we could do, then we can do it on the coming weekend. And this is really helpful. We don't have to write proposals, we can just do it. And on slide 7, I show a profile from one of these pulsars that are monitored regularly. This is now from my own data that were produced later. But what we see here has already been found by others, mostly by Stefan Oslowski, who I think is in the audience, but also by Jos Verbiest and others were involved as well. So what they found in this pulsar B158 plus 55 is that in addition to this main component that you see in the center, when you scale everything up a bit in the lower plot, you see 2 additional components, first echo and a second echo, at least that's the interpretation that they had. So what they found is that as a function of time, these 2 additional components seem to move relative to the main pulse. They seem to come closer to the main pulse and also become brighter with time. And the interpretation or the hypothesis was that maybe this is not intrinsic to the pulsar, but maybe this is just an echo, something happening on the way, some propagation effect, maybe something scattering induced or lensing induced. On slide 8, I show the typical geometry that, of course, you're all aware of, and I don't have to go into the details. And what we have to keep in mind is that the delay goes proportional to the square of the deflection angle on the sky, and everything scaled with the distance parameter. So the question is, we see this delay, can we measure the position offset on the sky with LOFA? And I heard about this echo, this ghost, for the first time 1 year ago when we had the scintillometry workshop here in Bonn. And I quickly went through the numbers, which are shown on the next slide, slide 9, where I made an estimate how large this offset on the sky should be. So we know what the delay is. We actually know pretty well where the pulsar is. It's at 2 kiloparsecs distance. And just assuming that the scattering is happening in the middle between there and us, we can estimate the deflection on the sky. And this would then be something like 0.14 arc seconds, or more if the screen is closer to us, less if it's further away. Now, this is slightly lower than the resolution that we have with the German LOFA stations, but we do not really have to resolve components, but we can separate them by doing pulsar gating. So we produce basically an image of the main pulse and an image of the echo, and then just measure the positions relative to each other. So we just have to measure positions to this accuracy. And this can well be done if you have enough signal to noise, which we do have because this is a very bright pulsar. And if this works, we can test the echo hypothesis if we see this offset, and then can use this offset to determine the distance to the scattering screen. And of course, a goal for later would be to use these 2 paths as interstellar interferometer. But that's maybe not even the next step, but that will come later. But we keep that in mind and also archive all the data to do that later. So on slide 10, I have a brief overview of how this works. So the VLBI in the so-called GLOW mode, GLOW stands for German Long Wavelength Consortium, so it's just the mode that we use to observe with our stations. In this mode, we can send all the raw data, the baseband data, to computers either in Bonn or Jülich, and we actually do it both, so we split the data volume. The data rates that we have to deal with are relatively high, so if we have all the stations, it's about 8 terabytes per hour, but we can deal with that quite well. After the observations data are transferred to a central computer in Bonn, where I can correlate them and then calibrate and analyze the data. On slide 11, I compare the advantages and disadvantages of working with our station in this way, because in principle we could also just do international observations with the correlator in Groningen. And doing everything ourselves has disadvantages. It's a lot of additional effort. We have to deal with these data volumes. But for this project, more important are the advantages that we have, and that's mostly the flexibility that we have in the correlation. So we can use special correlator modes, we can do pulsar gating, we can keep the data and correlate them again with different parameters, we can have arbitrary resolution in time and frequency, and that is really essential for this project, and nothing of this could be done with the central correlator. So we really have to go through this effort and do it ourselves. And because we can keep the baseband data, it's also relatively easy to add other stations. And as said earlier, we do that with this Kyra station, but we could also put in the GMRT or Algonquin if you like. On the next slide, slide 12, I show the parameters of the original observations. So we started with that just after the workshop last year in October. So the data that I will show in the following are 1 year old, unfortunately, but still interesting, I think. This was done again in what we call the high band low part. So that's the frequency range between 100 and 200 megahertz, and started in October last year. Originally, we observed this once a week. And what I show here is from the 11th of October. I won't go into the details of the calibration. If you are interested, you can ask me later. Probably better to do that offline. These last few lines is where all the effort goes into, so that's what I'm spending my time with. Very important is what's shown in the last line here is that we use the main pulse as phase reference and therefore as position reference. So on slide 13, I show interferometric visibilities on one of the baselines that we have here. So that's now folded with the known period of the pulsar. On the x-axis, we have pulse phase. On the y-axis, we have frequency. The upper plot shows the amplitude. So we see the main pulse and at lower frequencies, some hint of the echo. More important is the lower plot, which is the interferometric phases, the visibility phases. And we see that the main pulse has phases that are consistent with 0, of course, because that's how they were calibrated. But we also see the second component, which seems to have consistent phases, which are not constant, but consistent as functional frequency, and which are clearly different from the main pulse. So already this shows us that the position of the echo on the sky is different from the position of the main pulse. So this is really an echo, something happening on the way. It's not intrinsic to the pulsar. So this is only one baseline. On the next slide, I show results using all the baselines. So there I fitted a position of the component as function of pulse phase and frequency. So on the left-hand side, it's shown as functional frequency. The upper plot is the x offset, and the lower plot is the y offset. And again, at phase 0.5, we see the main pulse with 0 offset, basically. And then we see to the right of that, first echo, and a bit further right, the second echo, which both have consistent phases which are also more or less constant as functional frequency, but are clearly different from the main pulse. So we do see the offset of these two echoes. And since these seem to be constant with frequency, I averaged them over all the frequencies, which is shown in the upper right plots. So the upper one is the x offset, and the next one is the y offset as function of pulse phase. And of course, pulse phase here is a proxy for the delay, for the scattering delay. And we see, again, the main pulse flat around phase 0, flat at 0. And then a bit to the right of that, we have the first echo, and then the second echo. And of course, there are many points where the signal is so weak that we just have noise. So all these wiggly lines here are just noise. But what's interesting is that the points of the echoes seem to be aligned with this blue dotted line, which is a square root curve, which corresponds to the expectation from geometry. So this, or maybe it doesn't prove that the thin screen model is correct, but at least it's consistent with the data. And that's also not too surprising if you have something very localized. And from the amplitude of this curve, we can determine the distance, and it turns out to be about 124 parsecs. I don't have error bars on that yet, but this is much closer to us than the pulsar is, which, as said earlier, is at 2 kiloparsecs. And the plot below that shows the intensity of the profile, and the bottom plot is the intensity as function of pulse phase and frequency. So you see the main pulse being overexposed here, and we also see that the two echoes have very steep spectra. but apart from being steep, the spectra are very smooth, so I don't see any hint of a caustic or something like that, which is interesting. On the next slide, I show two images. These are actually dirty maps produced from the visibilities. What's most important is the brightest spot in each of these maps, which shows us the position of the echo. So the left plot is for the first echo, the right one is for the second echo. And all the other peaks in these maps are not noise peaks, but they are just side lobes. So they're predicted to be there, but they are not of physical meaning. And we see that both of these echoes are offset a bit relative to the middle of the map, which would be the position of the main pulse, where this small green spot is. And what's interesting is, first, the offset, the two offsets are aligned with each other, which is maybe not too surprising, but they are also aligned with this green arrow. And this green arrow shows the proper motion of the pulsar, the intrinsic motion of the pulsar. And it's not really clear why these offsets should be aligned with the proper motion of the pulsar, because the proper motion of the pulsar happens at 2 kiloparsecs distance and the scattering at 120 parsecs distance. So they should not be related to each other. And we don't really know why we have this alignment. It could just be a coincidence, of course. On the next slide, slide 16, I show one of the possible scenarios. So we could have just a compact localized cloud, and with some turbulence in it, then the position of the echo would just be defined by the position of the cloud. So if the cloud is not moving, the echo would be fixed. And if the pulsar is now moving along this green dashed line, then of course the pulsar would be moving, the echo would not be moving. And the separation of the two, this line would generally not be aligned with the proper motion of the pulsar. On the next slide, I show another scenario where we have something like a filament that is localized in one direction and can deflect radiation only in this direction, so perpendicularly to it. So now we have this filament along this red dotted line, and if now the pulsar is moving again along the green line, the echo would also move, and at some point they would meet each other, no matter what the orientation is. They would always meet each other in this scenario. But again, the displacement between the two would not be aligned with the proper motion of the pulsar. So this doesn't explain it either. On the next slide, I show the very popular model of similar effects where we see reflections of the sun by the waves of the sea. But such a scenario, which is pretty similar to this filament scenario, this doesn't explain the alignment either. So here we have all the images on the vertical line, but the proper motion of the sun, in this case, would be inclined relative to the horizon. So this doesn't explain it either. Now, earlier this year, on the next slide, slide 19, Mark Walker published an interesting paper about extreme scattering events in IDV sources. And he claims that these extreme scattering events may be caused by hot stars near the line of sight, or exactly by neutral matter that's being ionized by these hot stars, and therefore can produce very, very dense ionized media, very localized. And he tested that on 3 sources, so that's not a huge sample. But in these cases, his idea seemed to explain at least some aspects of the observations. You've probably seen images of the Helix Nebula, which I will also show a bit later, where we have these elephant trunk-like structures, which are very elongated. And Mark's idea was that these cometary tails or elephant trunks may cause lensing in the transverse direction. And
Olaf,
the transverse direction.
5 minutes left.
Yep. And the transverse direction, of course, can be predicted because he knows where the stars are, he knows where his source is. And this seems to fit what they see in the scintillation signal. So this is quite interesting. And even though I'm not completely convinced that this is the right explanation, but it's at least something interesting that should be tested. So on the next slide, I show if this can maybe help us to explain what's going on with B1508. And here, Mark Walker and Artem Tuntsov, who I think is also in the audience, helped a bit to find stars along the line of sight. There are 2 candidates that could be related to what we are seeing. The first one is relatively far away from the line of sight, 2.7 parsecs, and it's at a distance of 260 parsecs from us, so much further than what we think it should be. But the second one is closer to the line of sight, 1.37 parsecs, And from the best parallax that we could found, we get a distance of 120 plus or minus 8 parsecs, which is really close to my estimate of 124 parsecs. Even though, again, this can just be a coincidence, it's something that we should keep in mind in the interpretation of what we are seeing here. And on the next slide, 21, I show the relative positions of what we have here. So the background image is now from the Helix Nebula, just to show what the idea is, how these structures could look like. The pulsar is the red spot, and the arrow is the proper motion of the pulsar, and the star is in the direction of the white arrow here. Now, it could really be that these echoes are caused by lensing or scattering along the heads of these cometary structures. Who knows? In any case, we should be able to find out what's going on here, because we are monitoring the system continuously, and then we will see if the echoes are moving with the pulsar, if they are stationary, or if they're doing something else. So on the next slide, 22, I show the summary of what we've learned so far. First, quite important, doing VLBI with LOFA works, even if we do it offline. We can calibrate the data, we can deal with the ionosphere. It's a lot of effort, but it's possible. And about this ghost of B1508, we could clearly confirm the echo hypothesis. So these additional components are not intrinsic to the pulsar. They are produced on the way. We know where they are produced at a distance of about 124 parsecs, but we have this alignment with the proper motion that we don't understand. And of course, in the future, I want to do interstellar interferometry with that. Let's see if that's possible. The final slide, 23, is about the ongoing work and the outlook. So since May this year, I also include other stations in the project, in particular the core in the Netherlands. So that's a combination of many stations that can be added up together to form a very sensitive superstation, but also all the other international stations, and the Skyra station in Finland. So in total, we have now 14 stations, and we observe the system once a month for 3 hours, 1 hour per band. Most important is, again, this frequency range, 100 to 200 megahertz. Unfortunately, the data volume that we get from this is huge, and just moving the data around is quite some effort. But the data handling processing mostly works now. I'm still working on the implementation of exact astrometry, because that will be essential to see how everything is moving relative to each other and relative to background sources. The analysis, unfortunately, is lagging behind. So I cannot show any new results from the latest epochs, even though this is quite important, of course. If everything moves as I see it, or if the echo is stationary and the pulsar moves with its known proper motion, then the closest approach would be in a couple of years. So maybe something interesting is going to happen then. The one-line summary of this is that VLBI with LOFA has great potential for scintillometry. And I end with that. Thank you.
Thank you. Well, thanks for the very interesting talk, Olaf. We have time for a couple of questions, I think, so.
Okay, I can hear you very well. I don't know how well I could hear the audience.
Okay.
Olaf, very interesting talk. My name is Barney Rickett, and
Sorry, I cannot understand you at all. Could you get a microphone? Would that be possible?
We could repeat the question here for you.
Yeah, that's fine. Yeah.
I'll come closer. My name is Barney Rickett, and I'm a very interesting talk from you, Olaf. The offset in position between the main pulse and the echo, I didn't catch how much in angle that is offset.
It's about half an arc second.
So it's a large offset.
Yes.
In terms of scattering.
Yes, indeed.
And is that depends on the frequency? You've got a coverage of a range of frequencies. Is that angle independent of frequency?
In this frequency, it seems to be relatively independent of frequency. I mean, there may be some small effect of frequency, but it's not any whatever power of the frequency or anything like that.
Great, thank you.
Okay, another question? Willie, did you have?
Yeah, again, fascinating talk. If I